Okay, so this is the pre-lecture for Tuesday, February 9th, where we talk about climate change and reserve design. Now, I had originally put up this idea of movable reserves with the idea that people have proposed that climate change may require us to move reserves from one place to another. We aren't likely to cover that very deeply because there's not that much written on it and there's not that many places that that's actually a feasible option. But we will be talking about climate change and adaptation strategies. And so, for that purpose, I'm setting some background here and just talking about climate change and what to expect and what we ought to be thinking about as ecologists and conservation biologists with respect to climate change. And I'll start this by saying I gave a webinar to the National Park Service last summer, and that these slides are taken off of that. The webinar really got down to assisted migration, where I've done some work on that topic, and I was making the point that assisted migration is maybe the best bad idea, as the line goes in Argo, that there are other radical notions of thinking about how you might deal with species under changing climates. And I think I mentioned this in class, this idea of genetically engineering endangered species, for example. But first, a word or two about climate change. So this is the latest IPCC panel. It was in 2013. There should be probably one in 2017 or 2018. They're probably already starting, midway through working on it. This was the fifth IPCC assessment. They're very long and involved things because they take thousands of people, and all the documents have to be signed off by the participating governments. And the way that the notable changes in the fifth assessment, relative to previous assessments, is that we gave up these scenarios, the A1, B2, these kinds of scenarios of business as usual or reducing carbon consumption by a certain period of time, and have changed to expressing things in these RCPs, representative concentration pathways. And this graph on the right, I think, is emblematic of this kind of change, where the black parts of the line are history, how temperature has changed up to now. The different colored lines represent how much change we will expect to see by the end of the century, depending on how much carbon and other greenhouse gases we put up into the atmosphere. And so you see the dark blue is RCP 2.6, light blue is 4.5, RCP 6.0 is orange, and the 8.5 is red. And they just go further out this trajectory towards climate change. And the red one, RCP 8.5, is more or less what we think of as business as usual. It translates roughly very similarly. So okay, so that's what we expect in terms of climate change globally. Those are degrees Celsius on the y-axis, and how much warming we expect relative to the amount of anthropogenic emissions into the atmosphere. And so it's now making it a function of temperature by the driver, carbon dioxide, which makes a lot of sense. Placing an uncertainty around it, that's the shaded areas, and that then the length of the line represents those emission scenarios. And I think this is a kind of a nice way to look at this. So there's like three undisputed facts that we should all be very, very comfortable with in terms of thinking about climate change. And that is that global temperatures have risen by, one of them is that global temperatures have risen by about a degree centigrade over the past century. And this is based on temperature station data. And it is, yes, in fact, um, uh, um, adjusted for this idea that urban areas create heat islands, and we have expanding urban areas over that same century. Okay, so and the evidence of this is everywhere. That we have climate change, temperature change data all over the state of California. Sure, the Los Angeles and San Diego areas come up a little hotter than others, but so does just out on the coast in a relatively unpopulated area north of Santa Barbara. Glaciers are retreating worldwide, so there's plenty of otherwise physical evidence of global surface temperatures warming. That we have a reduction in summer sea ice extent, that there is a change in upper ocean heat content, so ocean temperatures are getting warmer, and that sea level has been rising. people have talked about a pause in climate change. If you look at the upper right of the upper right graph, you see that there was a period there from 2000 to 2010 where it looked like a pause. This, of course, is a statistically silly way to think about this, and that if you look at decadal averages on the bottom graph below that, you see that temperatures have been rising pretty consistently over the last century. Yep, and that's what I want to say there. Oh, by the way, that pause is more or less efficiently over, as 2015 was the warmest year in record, breaking 2014, which I think broke 2013. So I think we've had two or three of the consecutive warmest years on record in a row now. Okay, so the second undisputed fact is that carbon dioxide has risen from pre-industrial levels of about 280. This is detected in ice cores and things to about 440. Up to 400 parts per million in the air. Now this is comes from those famous sensors at Mauna Loa, Hawaii, that Charles Keeling started in the 1950s, 1958 to be exact, and that you can see the up and down pattern on the graph on the left of northern hemisphere photosynthesis, and that every year the carbon dioxide content will go down in the summer and up in the winter to reflect the seasonal breathing pattern of the planet based on plants. And that you can look back at ice cores, this is the graph on the right, and see thousands of years before today, so it goes back 400,000 years, and that carbon dioxide levels have fluctuated up and down, never getting above 300, and now we're above 400, and this is that part of the Al Gore movie where he gets on the crane and it lifts him up to emphasize the fact that it's way outside historic range of variability. And in thinking about this, the third thing we have to think about is this atmosphere of ours. It's just a very thin veneer surrounding the Earth. So down the lower right there, if you imagine that on the surface of the Earth you're driving from Davis to Dixon, you're already in the tropopause. By the time you get to Fairfield, you're at the ozone layer. And by the time you get to San Francisco, you're in outer space. So it's it's just not that thick. It's given the scale of the Earth, and we often draw it as it's seen in that lower right graph as this big fat thing relative to the curvature of the Earth. But you look at the Earth as a planet as a whole, and you see that it's just this very, very thin veneer, and that very, very thin veneer is critically important for making the planet habitable, so that you can have, say, there's ice on Mercury apparently. Because it has no atmosphere, there's no gas atoms that are bouncing back and forth, transferring heat from location to location. And so as soon as you get into the shade, it drops from several hundred degrees centigrade above zero down to below freezing point of water. And so that atmosphere is important in both trapping heat so we don't boil it during the day and freeze at night, but also so that all parts of the Earth are relatively warm relatively always. So this is that third component of the things that I claim to be undisputed scientific facts, and that is when people talk about who discovered climate change, I like to it's often attributed, or global warming, it's often espoused to Walter Brucker in '75, who suggested that burning fossil fuels could lead to warming. In fact, this was well known that the heat trapping capacities of carbon dioxide were well known long before that. In 1938, the British scientist Callender described how burning of fossil fuels may lead to the cessation of the predicted future ice age that was going to be on its way. Because remember, late 1800s, we were in a very cold period, what's known as the Little Ice Age, and in fact, it seems to be that that the initial burning of carbon through the industrial age may have, started that warming off. And he was able to do this because it was Svante Arrhenius in 1896 who described the functional relationship between CO2 gas and heat trapping capacity. And fundamentally, this is not has not been disputed. And in fact, if you take just the global change in mean average temperature, and then you ask how much it should have warmed based on how much gas we know we've put into the atmosphere based on Arrhenius's equation at a global scale, it's about spot on. Nate Silver makes this point in his book Signal and Noise. But of course, Understanding climate is a very difficult thing in that there's surface albedo and there's absorption by the water and by land. There's that different kinds of clouds have different impacts with respect to heat trapping, and so it can be very complicated. We also have Earth circulation patterns I'll talk a bit about that are really important for local expressions of climate, despite an overall global warming. So these structured observations of those temperatures lead to these conclusions that we got decreasing summer sea ice, et cetera, et cetera. But you know, one of the important things to think about here is that this warming isn't distributed evenly. So even though California has had a fairly big chunk of warming, so that the scale there in the deep reds is somewhere between a quarter and a third of a degree per decade of warming over the last several decades. But mostly that's in terms of nighttime lows, not so much in terms of daytime highs. And there's some peaks down there that are up at high elevation. And so it turns out that you can say with a fair bit of confidence globally that warming is maximized at high latitude during the winter months, at high elevation, and at night, all the times when, in fact, the Earth is the coldest. So it's raising minimum temperatures more than it's raising maximum temperatures, and that's pretty general. So heat trapping gases are increasing. We have complex models that should express that in terms of heat, and it should give us local expressions of these things. And we have a model that thinks about anthropogenic forcing, and that works considerably better than just other models like how much volcanoes or sunspot activity has changed temperatures. And so we end up with this picture of expected warming into the 21st century. Now, this is going to take two YouTubes, and this one's at 12 minutes, but I'm going to try and get through just the next two slides before I finish this. And that is that the global circulation models are really still very coarse spatial resolution and miss local climatic phenomena, and that this can be very important. So for example, here is a sea surface graph from July, I don't know what year, a model year, but basically what you see, that dark blue along the coast of California, is upwelling, and that records show that we've had increased longshore winds and increased summer upwelling over the last several years. And we've had a couple of years in there where San Francisco was unusually cold. Well, the coastal climate, as we know, is strongly driven by that ocean sea temperature. And you look, there's warm water a few hundred kilometers off of the coast of California, but that water gets much colder, and the air gets much colder over that. And so that you end up with this marine layer that flows onto shore and keeps California cooler. This is why Napa and Sonoma can grow grapes, and why I think it makes it really difficult to predict what might be the future of climate change's impact on grapes, because I think it has less to do with the global model than it does to do with what happens with this upwelling and the local expression of that in terms of our temperature. Because the global models are done at about a 1 degree cell block size, and so it's a pretty coarse thing. You look, you can see the degrees, latitude, and longitude on this, and each one of those big squares is about 6 by 6, so that's 36 squares. So you see a little square in there is, I don't know, well, I don't know, depends how big your screen is, but maybe the size of Yolo County, a little bit bigger. And so it loses a lot of the capacity for fine scale attributes, and it misses things like the Appalachian Mountains and upwelling along California, and these things are arguably pretty darn important. Okay, so I'm going to stop there and pick up with a second YouTube.